If you have the phone number for anyone who's skipping class right now because they have a bio exam, text them. Be like, this is going to be on the exam. This is going to be rough. All right. It's going to be rough if you don't show up. Okay? Chase. Okay, so why is Chase right? No, just kidding. All right. So on your worksheet, there is this graph. I want you to fill in those things that are listed there. Everyone do that? So at the very top, it says, on the figure to the right, label the following. Energy of reactants, energy of products, transition state, change of energy, activation energy. Go ahead and fill all those out. You guys have seen this on Sapling a couple times already. So take the next 30 seconds to 1 minute to fill all those points out on your graph. And we're going to fly through these next questions that involve those.
I was answering the question.
No, not answering the question. We're filling in these things right here. So put these 5 different things on this graph. All these terms right here. Come on there. All right, a couple more seconds. Okay, so I really want you guys, what I wanted you guys to do was to complete all the labels on this graph. Where is the energy of reactants? Where's the energy of products? Where's the change in energy for the reactants to products? Where is the activation energy? So we're going to assume that everyone did that, even though not everyone did. Okay, so you're going to use those to answer the next set of questions, all right? Is that what everyone had? We start out with our reactants. The coordinates mean we start left, we go the direction of the arrow. That's what a reaction coordinate diagram tells us. In this reaction, what is more stable? Our reactants or our products? We start out our reactants, we end at our products. It means we're more stable afterwards. They're lower in energy than our reactants. And then the next question, Ms. Darrow? That it is what?
One direction.
Yes. This reaction here, hey Gus, you all right?
Yeah.
Thanks for joining us. Thanks, Dan, for texting them. That the way that this reaction coordinate diagram is stated is that it is going from left to right. The reaction can occur in both directions. We'll be talking about equilibrium next week. But for this reaction, the way that it's drawn here, we are talking about specifically from left to right. That is the direction the reaction goes. So thank you, Mr. Okay, so then the next question is, which of these is the highest energy state, also known as most unstable? Is that you done the whole thing? All right, closing out. So why is the transition state the least stable, the most unstable, Katie? It has the highest energy. It is the place where we're not going to stay. Why? What are those atoms? So if we're between reactants and products and we're in the transition state, what is happening to the bonded atoms at that state? Kira?
The bonded atoms are either breaking apart and making new bonds.
Great. They're in the process between making new bonds and breaking those, so they're in that process where they're being torn apart. Why do atoms form bonds in the first place? Stability. So if two atoms are bonded together, they're more stable because they help each other fill each other's octet. If we're in a place where they're now being broken, they're in a transition between that, and that means they're incredibly unstable, and they're going to rearrange in order to form a stable product to have bonding groups there. So then, which is the most stable in the reaction shown here, the reactants or products? Click it in. Jose, did you grab a worksheet? I imagine that this is going to be relatively quick. Products are most stable. They release energy from the transition state to the products. Taylor?
I have a question. So if radioactive isotopes are unstable, why don't they react with anything? Why don't they combine with anything?
So they become more stable by releasing something or by converting something. So we'll be talking about that hopefully at the end of class if we can go at the pace I want. So, good connection. Okay, so which of the two arrows represents the change, total change in energy from reactants to products? Everybody in? What do you guys think? Michelle, did you change your answer?
I put A, but I know it's B.
Okay, so why is it B?
Because the reactants start at the dotted line, like that's the energy of the reactants, and then the products are below it, so
So what is the arrow representing for A then?
that's the activation.
Great. And I think that would have been the next question. All right. So activation energy, that's how much energy needs to be put in order to allow the reaction to proceed in either direction. And B, that difference between the reactants and products, that difference is the total change in energy for the reaction or the difference between the reactants and products. So for today, my goal is for you guys to talk about, now that we have a basis for discussing a reaction and energy in a reaction, you guys are going to be responsible for saying, well, how does temperature or activation energy affect that diagram that we just talked about? And in order to help us do that, we're going to be talking about the Arrhenius equation, and we're going to be using that to qualitatively, that means without numbers, describe how temperature affects the rate of reaction, and quantitatively, which means we're going to be doing calculations, determine the relationship between the variables of changing activation energy and using all of that to describe how our rate constant can change with activation energy changes and temperature changes. So last class, the very end, I showed you the Happy Gilmore video. So the Happy Gilmore video, I did that because one, it's really funny and stupid, but two, this is a reaction coordinate diagram. What was the analogy with the Happy Gilmore thing that he was talking about? Clown's tongue is this part here, right? And what was trying to get up and over it?
Golf ball.
So we had the little golf ball. And, okay, his was being blocked more than not having enough energy. But if the golf ball doesn't have enough energy, what's going to happen? It's going to stay back on this side. Once it gets enough energy, then we're going to be able to get up to the transition state, the most unstable point, and then it's going to have a decision whether it goes towards the products, which is more stable, or in the other direction. And so in order for a reaction to occur, for that golf ball to even be considered in this, that amount of energy required has to be, there's a few qualifications that have to occur. In order for two molecules to react, they have to collide with each other. If they don't run into each other, then no reaction is going to happen because new bonds are going to be formed and no bonds are going to be broken. We need enough energy to react, which means we need enough energy to get up to the transition state, and that if two molecules are going to react in order to form a new bond, if they don't run into each other in the right orientation, we don't have a carbon and oxygen running into each other, and that's what we need, then that reaction is never going to occur. So let's have that molecular view as we're thinking about how reactions happen or don't happen. So let's have a little bit of a teaser first. Everyone put in their opinion? Okay. So most of the people say as temperature goes up, activation energy goes down. We're going to revisit this in a little bit in class, and I want you guys to be able to justify why or why not temperature has an effect on activation energy in a little bit. So to do that, let's look at a reaction between chlorine gas and the NO radical. So I'm showing those two molecules here. Chlorine gas is in the top left, NO is in the top right. And that is the reaction coordinate diagram for this reaction. So what we're going to be talking about is as those molecules come together, we hit a transition state. Does everyone see where the red line is representing where we are in the reaction? And the question that I want to start out with is, what is the most likely outcome from this transition state? You can talk to your neighbor if you want in order to decide which is the most likely outcome. What do you think, McKenna?
We think products will form
Why?
because it's already at the transition state, so it's like already has the energy.
So think about the Happy Gilmore analogy. Okay, so can anyone describe this to me using the Happy Gilmore analogy?
When he hits the golf ball, it can either go up or go all the way over if he does it with enough force, or if he doesn't do it with enough force, it could go back to the ground.
Okay, so if he hit the golf ball, has anyone ever done this in mini golf? Where you get the golf ball to right here, what happens? Does it always go to the product side? No, there's an equal 50-50 chance. If you don't hit it hard enough and it just has enough energy to get to the transition state, all we're saying is that now it has an equal shot at both sides. Okay? So the two cases, case one, would be where we get exactly what we started with back, right? That's a possibility. It's just as plausible as the second scenario where if we're at the transition state and the new bond forms and we end up with the new molecules being formed. Taylor?
But is this a reactant being formed again, or is this not being used?
Well, if we get to that transition state, then it means that bonds are being broken, but then they're being reformed, and we end up exactly where we started. So it's a little bit of semantics, I guess, in that case. But I think that was answer C, right? That it's just as likely to go in either direction if we're at the transition state. So then, would this transition state even occur if we had that NO flipped in the opposite direction? Talk to your neighbor. Going back to our original way of showing this, could this transition state occur if the NO was in a different orientation, if NO was turned around so that N was in the top right and O is in the bottom left? Sabrina, you want to share your thoughts?
I said no, but if the N was on the left side, then you have to switch to the other side. So if it isn't on the N, you have to hit other collision.
Yeah, so it's really important not only that the molecules are there and that we have enough energy, but that when they collide in a manner in which the two atoms that are going to react are actually colliding with each other. So that term that we use is orientation, that those atoms line up with each other in a manner in which they are likely to react. And when you guys start taking organic chemistry, or if you've already taken organic chemistry, then it even becomes more complicated than that. It can't just be anywhere on that chlorine atom that the nitrogen collides. It has to be certain places where it interacts with hybridized orbitals, and it interacts with the anti-bonding orbitals, but you guys will be dealing with that organically. Okay, so we need to be thinking that they need to have enough energy to get to the transition state, and they need to have the right orientation in order to have that transition state occur. So then I want you to really focus on this graph here and where that red line moves left to right. How is that going to change when we increase the temperature? So answer this question first, and then there's another one about it. So everyone says, except for one, that when we increase the temperature, that a reaction speeds up. All right, I agree with you. I totally agree with you guys. So then the question is, let's go back to the question you guys just had a minute ago. When we increase the temperature, why does the reaction speed up? So go ahead and answer this clicker question. It's also on your worksheet. And then I want to hear a discussion as to how you can justify your answer. Mommy, can you scoot back a little bit and let Sarah kind of join in?
Is this one of those trick questions where they're both right? No?
3, 2, negative.
All right, has everyone clicked in your thoughts? Yeah. Mommy, you want to share your thoughts on this? Okay, Brian, what are your thoughts?
Well, yeah, activation energy increases, and so there will be less to go over.
Okay, wait. So let's think exactly what we said. So if activation energy decreased, then what would happen to that graph? What would be different about it? Maybe can you draw it? Okay, so the activation energy would decrease. Is that what happens when you warm a sample up? Sarah, what happens when you warm a sample up? Your molecules speed up, but your reaction doesn't change. Taylor, you want to answer that?
No.
That was what you wanted to say?
No.
What did you want to say?
I was going to say that I thought that the activation energy would decrease because when you add heat, it's like adding energy, so that it would be like energy for the reactions that are using less for the reactants.
So let's go back to our Happy-Gilmore analogy. So I think we're mixing up a couple things that we're talking about here. In a Happy-Gilmore analogy, what is the equivalent of a hotter reaction, increased reaction temperature? Nice and loud?
Hitting the ball harder?
If we hit the ball harder, does that mean that this hill gets smaller? No. One of the biggest misconceptions, I think, that we start making when we pair up temperature and activation energy is that the height of this, which we know is activation energy, changes based on temperature. But it doesn't change at all. There's no change in this whatsoever. What happens is that if these molecules have a lot more speed, if their temperature is increased, and the ball is hit harder, then there's much greater chance that that ball is going to go up and over that tunnel, unless the teeth come down the cloud, of course, and then we can't really make those predictions. But that's Schrodinger's cat, and we're not going to worry about that. So, what we're really talking about is that more of our molecules have enough energy to overcome that activation energy. And activation energy itself is completely unchanged by temperature. So then what has an effect on activation energy? Well, a catalyst. If we add a catalyst, an enzyme is a form of a catalyst, then how does that change the activation energy? Okay, so enzymes bond with substrate, form products. Thomas? It decreases the activation energy, but how?
It takes like the stress load off. It's doing more work.
Okay, so it somehow does some work. Pat, you want to add to that?
It's the molecules that alternate the way they interact with each other.
Yeah. So typically what we see when we have a catalyst is instead of having one hump like that for the activation energy, typically we'll have two, which means that it actually forms an intermediate. And what that does is it gives us an alternate path to get to the same products, where we have our lower energy intermediate that we can go between, which means that the total energy needed to get over those two barriers is, we're not talking about a sum, right? As long as we have this much energy, we can get over both of those barriers. So an enzyme brings molecules together, and it actually pulls on bonds a little bit in order for the reaction to occur more quickly. Catalytic converter has gases come out of our car, interacts with platinum. It lines them up perfectly so they don't actually need to hit each other so quickly so that they can react with lower temperatures. So the equivalent here would be, if we increase temperature, what we're doing is we're not changing the mechanism of the reaction. We're only changing the speed at which they collide, which means that now we can have the reaction go much more. The reaction is able to overcome activation energy. So what do you guys think about this statement question? Activation energy to convert between products and reactants, and between reactants and products, is the same.
Are they drawn to scale?
I believe these two are drawn to scale. So this is now talking about if we had a reaction coordinate diagram, if we looked at the reaction coordinate diagram, or we flipped the reaction coordinate diagram. Let's do another 15 seconds. Hannah, what are your thoughts? You think that the activation energy is the same in both directions? Can you circle the activation energy on these two graphs? Okay, so would anyone like to do the Happy Gilmore analogy for this? So would anyone like to use the Happy Gilmore analogy for whether it's the same energy to go in both directions if the activation energy is the same? Demetrius?
Would it tend to be like there'd be more energy trying to hit the ball like downhill than like uphill? Like so like for instance like some reactions require more energy to like break your bonds and then some require a lot less to break them. So like going back to like endo and exothermic reactions, like some reactions require like less amount of energy to break them rather than to form them.
So if these are our two versions of the same reaction here, one is going in the forward direction, one is going in the reverse. Which is endothermic and which is exothermic? Talk to your neighbor. Which is endo, which is exothermic? Okay, so raise your hand if the left one is endothermic. Exo? Damn. That means that in order for this reaction to proceed, exo means outside. It releases energy to the outside. This is the amount of energy it releases to the outside. This one, you need to put energy in. The total change in energy of the reaction is energy in. Both of them require an input of energy though, right? You still need to input the activation energy in order for either one of these reactions to occur. And so what I like what Demetrius was saying is that in order for this reaction to occur, breaking these bonds is much easier. These are probably single bonds. And then we form maybe double bonds. These bonds are much harder to break, and hence are much stronger, more stable, and they release energy in the process. Here, we're talking about breaking double bonds, which requires a hell of a lot more energy, and then we're only forming single bonds, which are weaker, which release less energy when those atoms come back together. So I really like how you phrase that in terms of the strength of the bonds. And I believe that most of our class agreed. So the directionality of a reaction plays a really big role in whether how much energy is required to activate that reaction in order for it to go forward. All right, so if we zoom in on one of these, and what is this H? I have E all over the place. What is this H? Enthalpy. Us chemists, we don't really like to talk about the change in energy because the change in energy or Gibbs free energy requires us to talk about entropy. And entropy is really hard to measure. So we kind of make this generalization that the change in energy, well, if we measure the heat lost or gained, endo or exothermic, we can kind of say it's the same thing. Yeah, so it's a real oversimplification. So at the end of the semester, of this semester, we're going to be digging into that and basically saying that that's not the whole case. But for a lot of chemistry, you'll see interchangeable enthalpy, H, and energy. All right, so really what I want to point out is just that if you're going from reactants to products or products to reactants, so that is going to be a very different amount of energy that can be required. So then what about the change in energy? Everybody in? Almost? Pauline, you want to share your thoughts on this?
I said that the increase because bring it on the graph, that if there's just a higher temperature, the reactants would be at a higher starting energy, and then would go through the transition state. And I guess I was assuming.
You want to draw something?
Yeah. Okay.
So why did you leave the energy of the products the same?
Now I'm realizing that I'm not sure if I can just do that.
Okay. Someone else want to take a stab at explaining it? Taylor?
I thought that it would decrease with increasing temperature because then you have molecules moving faster, so they would have more energy, so they'll go over the activation energy easier.
Okay, so what you're getting at is how many of the molecules can get over the activation energy. The question is asking about the total change in energy of the reaction. Val? Why would it be the same?
The reaction just went faster. The total change in energy is the same reaction. It's just
If we have a combustion reaction, is carbon dioxide, so let's say we have octane and oxygen on this side, and on this side we have water and CO2. We're not talking about how many of each. Does the energy of water and CO2 relative to octane and oxygen change based on how hot it is? Those molecules will always have a certain amount of energy required to break their bonds, and the relative energy between the two will always be the same. The only thing that changes is, like you said, how many of those molecules are able to undergo the reaction and overcome the activation energy and then release or absorb that total amount of energy. So I agree with the majority. What was our majority? I don't know why it's so small. 66%. Please talk to your neighbor. Make sure you can answer this. Doesn't mean that everyone got it. Doesn't mean that everyone got it.
That's what I answered. I thought that the other question was talking about this.
Yeah, well, change in energy is very different from activation energy. All right, did everyone agree with your neighbor? Check and make sure that someone else agrees with you that you're sitting next to. All right, everyone agrees with your neighbor. Does anyone not agree with your neighbor? You don't agree with what? Why? What's wrong with the question?
Well, I guess you said earlier that activation energy doesn't decrease.
Hold on, guys.
Temperature.
Can we hear what did you guys? Go ahead.
Earlier when you said that activation energy doesn't decrease because of temperature in the earlier question, but the equation has activation energy divided by RT, which is temperature, R times temperature.
But does that say that one change will result in a change in the other?
If you're, no, it's not.
Nope. All right, so we're going to dig into that. We're going to dig into the Arrhenius equation, which allows us to mathematically compare these. So I'm beating a dead horse here, but it's really important that you don't think changing the temperature is the same as adding a catalyst. Those are two incredibly different things. So let's think about what actually is happening. We have molecules moving around. Molecules are colliding with each other. We can think about gas a lot of times. So if we have a sample of gas that's at 45 degrees Celsius, what is true about the speed of the molecules? Yes. All the same gas. Thank you for clarifying. So, Jose, I want to hear your thoughts on this, Jose.
I'd say they're all moving the same speed.
Okay, does everybody agree?
No.
Sarah, why do you not agree?
It just makes more sense.
Does anyone?
It's not, they're not moving, and for all of them to move at the same speed, I feel like is unrealistic. All of the gas molecules are not going to move at the same speed, so I would say they kind of.
Okay. So I like that you just can't picture every single molecule of a nitrogen gas, say, moving at exactly the same speed. It just.
They collide with each other too, like their own.
So even if there are elastic collisions, it means the total energy is conserved, but individual particles, some might be moving faster and some might be moving slower. So I agree with you, and what I'm going to ask you guys to do now, and I think, what was that? Oh, wow. Did not expect that. Hold on, let's go back. Close, go back. Does anyone want to try to explain this a little bit more then, since it seems that we were not in agreement? Justin?
I remember we were talking about this before, how there was a distribution of like slower speeds and faster speeds, but then there was like overall like maybe an average speed for most of the particles like of the gas.
So if we warm up the temperature, what happens to the average speed?
It would move over to the average would like transfer over to a higher speed.
So we shift the relative speed of all the molecules to faster, which means that we have overall a faster average. Agreed. So go back to gas laws. This is what I want you guys thinking about. So we talked about this for gas laws and for particles moving in a solution as well. So on the back of your page, you have two plots. On those two plots, I want you to draw. One is, I think, a sample of gas at, let me see what I said here. One is at room temperature, and the second is at a higher speed. I want you to draw higher temperature, aka a faster speed. I want you to draw what that distribution looks like at a lower temperature and how it looks different at a higher temperature.
complex.
There's distribution molecules.
That's it.
In this one, some faster, some slower.
Wait, Dr. Bailey, should I draw both or just one?
How about you draw one for now? Thanks. Okay, so we have Kristen's drawing here. Kirsten, can you describe what you drew?
It's a bell curve.
Okay, so you have some sort of bell curve. And what we find is when we look at actual gas particles, we find something a little bit different, and we find that it's skewed. And so let me show you guys a little example here. So we have this, oops. So we have this little cute JavaScript that we can play with. It's linked to the slides. And so what I have here is a sample of gases. And we can add more gases if we want. What do you guys notice about the relative speed of all the particles? Let's add some more. Okay, so one, they're different speeds. And are there any that are standing still? No. They get close though, right? There's a couple that when they collide, like that guy was going really slow for a second. Then you can see that guy, right? Get my hand hit by these things. So then let's raise the temperature. What's going to happen? Are there still some particles moving very slowly at some times? Okay. So then what are we going to draw for our second graph? And this is the first graph where it's colder. Can someone draw on top of this what the second graph where it's a little bit warmer would look like? Anyone? Scary iPad drawing? Thanks, Mia. Okay, thank you. Would anyone make any modifications to what Mia drew? Alex? Okay. So why would the beginning of the line go all the way back to here? Absolutely. So we saw from that little simulation, which helps us actually visualize what's happening, that even at extreme temperatures, there's still some molecules that are moving really, really slowly. And there's actually one other modification I'd make to Mia's graph. Anyone want to venture to make a guess? Chase?
Well, right now it looks like the latter reaction, like the faster one, has more particles because of the area underneath the curve.
Okay, so just to be a little bit more accurate, the area under the curve kind of tells us how many there are. And so we'd probably have something like this. So there's going to be the same, we're saying that we have the same sample of particles at a colder temperature and a warmer temperature. And that the total number of them would be the same. And if they're spread out over a larger range of speeds or molecular energy, then that means that there would be a lower peak. So it's really, that's a little more technical detail, but I think it's important to point out. Okay, so let's say this is one of the two gases that's reacting. How would we talk about where activation energy might be on a graph like this? How would activation energy come into play? What do you need in order for a reaction to occur?
Collision.
What's that?
Collision.
We need a collision, but not just a collision. It has to be the right orientation and enough energy. So what we'd say is if any reactant, that was a really bad straight line, wasn't it? Let's do that instead. If any molecule had more than that amount of energy and collided with another molecule and had the right orientation, that would be likely to overcome activation energy and then be able to react. So talk to your neighbor for a second. Try to describe what fraction of the colder versus the warmer sample would be able to react. So that is the minimum energy required to react. So how does the two So the question is, if that's the amount of energy required to overcome the activation energy, then can the colder and the warmer sample both overcome activation energy equally? Or what's the relative difference between how they... Tatiana, you want to share your thoughts on this? Salma? So let me restate the question. The question is, if we have two populations of a gas, the blue one is at a colder temperature, the red one is at a warmer temperature. The green line represents the minimum amount of energy required to overcome the activation energy. How do those two samples differ in their ability to undergo this reaction? Shane?
Only a little bit of
Can you maybe shade in the part of blue? So as Chase was saying, the area under the curve, that talks about the number of molecules, right? So in the colder sample, what percentage of those total molecules do you guys think could react?
1/10.
Maybe 10%, maybe less. Okay? Then Claudia, how would you represent the amount, or the fraction of the red, warmer sample that could actually undergo this reaction?
This is so weird to draw on.
You don't have to fill it in completely.
Yeah, there you go.
Overall.
Yeah.
What about the part that's under the blue there? Is that also...
Oh wait, just kidding, I'm lying. Wait, what?
Undo it there.
Wait.
So the question, maybe the part that had already, that's so terrible, you can't see that arrow, can you? Everything under that red line that has more energy than the activation energy, if it runs into another molecule that it can react with, and it has the right orientation, it means the atoms that need to collide do collide, then those can react. So then, how is it that temperature changes the rate of a reaction? Because we know temperature increases the rate of reaction, so let's go back. Let's try to restate that. How does changing temperature affect the rate of a reaction? Claudia? Okay, there's more collisions, and what else? Cosmo?
So there's more molecules reacting.
There's more molecules reacting, but why? Justin?
There are more molecules that have potential to react because they exceed the energy needed.
Great. So it's all about relative to the activation energy. In the colder sample, there is a much smaller fraction of the molecules even have enough energy, if they were to collide, to overcome that activation energy, to get over that hump. But if we put a lot more energy in, it means now we have a ton more, we have a much larger fraction of the molecules that can overcome that activation energy if they are in the right circumstances. So what fraction do we think that the warmer sample has that can overcome the activation energy? Pat, what's your guess? Yeah, it looks like it might be about 50%. Wouldn't it be nice if we had an equation that let us actually calculate that?
Yeah.
What would that equation be, Chase?
Would it be, what is it called? It's on the back of the page, right?
Okay, we call it the Arrhenius equation. It's called the Arrhenius equation in Swedish, but same difference, right? So Arrhenius was a Swedish physicist / chemist who actually was able to quantify the relationship between how changing of a temperature influences the rate of reaction. So how does that fit together, though? What is the Arrhenius equation? Actually, I can write out what's on your page there, right? So I just said, how does temperature affect the rate of reaction? This equation doesn't have rate in it at all. So I want you to talk in your group and try to figure out how that equation helps us relate how the change in temperature affects the rate of a reaction. So how does that equation help us determine how a change in temperature affects the rate of reaction? Figure it out. Talk to Sarah. Yeah. How would it affect our change? Who knows? What's it our? I'm guessing you guys didn't read this part of the chapter. All right. So, Val, what is K? K is our rate constant. So then if we know that increasing t, it's making the negative exponent bigger, the denominator of it bigger. So then if we increase t, then k increases. So how does that tell us then the rate increases? How does that work? So we know that changing t changes k, but how does changing k affect the rate? What relationship do we have that allows us to say how the rate is influenced by the rate constant?
Like if you have a faster or a higher rate constant, then you'll have a faster rate of reaction.
Yes, very true. What rate law? Right. So we're trying to tie all these things back together. That so far we've talked about how time influences concentration, integrated rate law. We've talked about how changing concentration of the initial reaction changes the rate of a reaction. And then now we finally have a tool that says, well, what if I had a catalyst? How does that change our rate? What if I change the temperature? How does that change the rate? So everything we've done up until this point has assumed that there's no change in the reaction mechanism, that the catalyst is not changing between our different times of looking at it, and that they're all at the same temperature. But we know that's not true. Why do our bodies not function if we get below 93 degrees?
Enzymes don't function.
Why do enzymes not function?
Because they're really, well, they have to have, like, their form will, like,
So
the activation site for the substrate will, like, be messed up from the bonds messing up in the enzyme.
I'll give you a hint. Cosme?
I was just gonna kind of feed off of what he said. Like it'll change the activation site, so they'll get tinier, they'll get smaller.
It might. It might not. Claudia?
There won't have enough energy to overcome the activation energy.
The reactions that we need to sustain life, just a small decrease in temperature will have a drastic effect on reactions being able to proceed or not, even if they have a catalyst. So that small change can affect a lot.
Generally, from what I know from biochemistry, 93 degrees isn't quite enough to denature the proteins that change the active site. So just be careful with that.
Yeah, so if we were to heat up a sample and we go maybe 10 degrees above body temperature, then that starts to get enough where we have a lot of vibration going on and they might not hold tight together. When you cool things down, typically those, and if anything, become more stable, and they need that flexibility in order to have reactions occur. So I would agree that we should not say that those molecules don't break more frequently if they're cold. If anything, they don't break enough, which means that our chemical reactions don't occur instead of occurring too much. Okay, so let's everyone clicked in? Come on, Taylor. Didn't work at all, did it? There we go. All right. So what do we say? As the temperature of a reaction goes up, the overall fraction of particles with enough energy to overcome activation energy, Alex, is? Mr. Wolf? I'm reading the question out loud, buddy. Come on, help me out. Do you guys agree? Okay. So if we go back to that original image that we had, and I'm hoping it's just because I put you on the spot, Alex, I'll give you a benefit of the doubt on that one. We're increasing the fraction of the molecules that can overcome our activation energy. This is the image that you have in your book and many other books. When I showed this graph to start with, people get so confused because what are the different colors? Why is some shaded? Why is some not? So since you guys are somewhat familiar with these two graphs, these are two graphs of two different temperatures. What's going on with these two lines? Can you guys talk to your group? Try to figure out what they're trying to represent with those two vertical lines. Can you guys see it all right? So what are the two lines? Well, how's there different activation energy then? What's that about? What? Okay, you guys gotta talk to each other, figure that out. So what are the two lines showing us? Okay. So why is there two different activation energies? Because there's two different what? There's a lot being shown in this graph. The two different, the yellow and the blue. Okay, so I need you guys to talk about what shows two different temperatures, and then how that relates to activation energy. There's a big difference there. Okay, so what do the two different colored lines represent? The top, which is purple, and the bottom, which is yellow. What do those two different lines represent? Two different temperatures, the same sample at two different temperatures. So then why are those two activation energies at different points? What are those trying to represent, Pat? So careful, there's 4 different things being shown here. There's 2 different temperatures, and then there's 2 different activation energies. Shane? Which one has the catalyst? So I want you guys to be able to produce graphs that show what does the population change look like of the speed of the molecules if we have a different temperature. What is different about the graph if we add a catalyst? Those are 2 incredibly important things that they kind of overlaid double on this graph, and I'm not so happy about that. But I need you guys to be able to draw your own versions of that. I heard a number of people say that the activation energy goes down because we increase temperature. What's wrong with that statement? Okay, it's not true. Why? Why is it not true? What's that, Pauline? Temperature has no effect whatsoever on activation energy. The 2 are independent. We can both lower the activation energy and warm up a sample if we want to increase the rate of reaction. The one does not affect the other. So hopefully this is somewhat familiar when we were talking about a sample of gas or a sample of liquid that has to warm up to get enough kinetic energy to overcome intermolecular forces to go into being a gas. Right? If you have a colder liquid sample, it means that less of the particles are going to be able to go into a gas. If we have a warmer sample, the orange line, that means that more of that sample is going to be able to have a phase transition and go into being a gas. And so we didn't go too much into vapor pressure, but that's a bit of this discussion as well, was talking about vapor pressure, and even before we boil, how much of a sample is in a gas part of the gas state. So this simulation that we had a minute ago does not only show gases moving around. Reset. But it can also show a reaction. So let's show, where are our options? So there's a chemical reaction that occurs. You can see the chemical reaction at the bottom of the screen here. A plus BC gives AB plus C. So let's add some reactants. Let's add some of A. And then let's add some of our other reactant, BC. So how many reactions are occurring? So far, none. What could we do to increase the likelihood of those molecules reacting? Could increase the concentration of B. Okay, so let's try doing that. So there's a lot going on in this interactive simulation, right? So we show a bar graph of how many, We can actually see them moving around, and we can see the potential energy diagram. Should any have reacted based on where we are, the total average energy versus the activation energy? Should anything have reacted? So I hear no, and I hear it could have. It did. Okay, so how do we justify, how do we rationalize that a reaction occurred, even though the total average energy is way less than the activation energy? Justin?
Well, when we looked at the graph, we still had a group of molecules that had the speed to reach a reaction.
So everything is not moving at the same speed?
Yes, there are some molecules that are fast enough that would be able to make a reaction possible.
So we need to think about that this green line here is showing the total average energy. It's not saying that some are going fast or slow. So then what else can we do besides increasing the number of BCs to make this reaction proceed in the forward direction? Javante? What would that do to that green line? The total average energy green line. Right, raise it up. So let's try. So let's add some fire. So what happened? Do we have molecules that are still basically standing still? We have some. Do we have any that are moving faster now? We have a lot that are moving a lot faster, right? So let's raise it up even warmer. So if we heat it up as hot as it can possibly go, why do we not form all products? Alex?
Because it has the same probability of going to products as it does of going back to reactants.
So if we have infinite energy, then there's no benefit on being on one side or the other, so it's just going to be going back and forth. And so that's something we're going to be talking about in equilibrium, is if we have a little bit of energy or if we have a lot of energy, where is this reaction going to settle? Notice it didn't go to 50-50 though, because we had more of one of the reactants. That might push it more towards some of the products. And this is what we're going to be starting next week, is to calculate where this ends up settling, is what the relative concentrations of everything are. So the simulation is attached to, it's linked to one of the PowerPoint slides. I'll post those online just after class. I highly recommend, if you want to wrap your head around this, to see how all these parts fit together, check this out. It's a JavaScript, so you actually have to click on it, download it to your computer, and then you run it on your computer. It's pretty straightforward to do, but if you can't figure out how to do it, just let me know or come to office hours. All right, so we have activation energy and the rate of a reaction. So with all of these reactions, all of these equations we've been using so far, we have not yet shown how activation energy directly affects the rate of a reaction. So that's what we're going to be doing now, is that Arrhenius equation through the rate constant, the same rate constant we see in half-life, integrated rate law, differentiated rate law, in all of these equations, that rate constant, the way that it is influenced by temperature is described by the Arrhenius equation. So let's mess around with this a little bit. Everyone clicked in? So let's go one at a time. What relationship does the differentiated rate law allow us to explore? Megan? Differentiated rate laws, we have a lot of them, right? Zero, first, second order. Brianna, what do they allow us to explain relationships between?
Like rate order and rate constant and concentration.
Okay, so concentration, and we can the rate order helps us relate that. What are the two major things we're comparing? What influences what? Mia?
Rate and concentration.
The rate of a reaction and the concentration of the reactant. That is what a differentiated rate law allows us to do. Rate order influences how that relationship exists. What about an integrated rate law? Michelle? What do integrated rate laws allow us to compare or work with?
When you introduce time,
Time and how it influences what?
the reaction concentration.
So an initial versus a final concentration and how time plays a role in that. And then Arrhenius equation, what is that allowing us to explore? Javante? Temperature affects the rate constant, which then affects the rate through other relationships. And not just temperature, right? What's the other thing?
Activation energy.
And the activation energy. Okay. So both of those are explored through the Arrhenius equation. So that means that this is only C. How could you argue for E? Javante?
Because if you're using the Arrhenius equation, it's like giving you K, and then you need, and then K is in like the differentiated rate law, which would tell you how concentration and rate are related.
Okay, I like that answer better than mine. I agree with you guys. So in order to say how temperature affects the rate of the reaction, you have to use both of those. Good call. So let's go back and let's change correct answer to the more complete answer. All right. So we're going to zoom through these next set on catalysts. We've already talked through it in the earlier part of class. Another 5 or 10 seconds. Thomas, you ever feel like you're taking a nap? All right, closing out. So the really important take-home from this, did the initial energy of our reactants change when we added a catalyst based on this diagram here? Sarah? Did the initial energy of our react? So on the right is a graph of a reaction without a catalyst, which is the blue line, and then the bottom red line is with a catalyst. Did the overall energy of our reactants change? Brian, where's the energy of our reactants on this coordinate diagram?
Energy of the reactants?
Yep.
Right there.
Where's the energy of our products?
Right there.
Okay. So what I wanted to point out is when we add a catalyst, the in-between changes, but not where we end and where we start. Can you guys see that? So the analogy that they like to use, let's not do that question, let's do this, is how much effort does it take to get from one place to another? If you climb up and over the mountains versus if you go around on a smaller mountain, it doesn't change where you start and where you end. It's just how much effort goes into getting between those can be decreased by having a more efficient way or a catalyst that helps get us there.
So with a catalyst, it doesn't make the reaction go faster, it just makes it have less, like, you just have to put less energy after the reaction happens.
Okay, so I like the way Taylor said this, and let's have a discussion about this. Does adding a catalyst not increase the rate of a reaction? It only decreases activation energy. That's what you said, right? Does anyone want to counter that or say it a different way? Thomas?
Catalyst is going to decrease the amount of energy needed for the reaction to take place.
True.
Between molecules.
Then does that mean that it doesn't increase the rate of a reaction? Those two statements you said, right? James?
Since since the activation energy is decreasing, if we have our graph again, that line's moving, so more of the area under the curve is now able to change, so it increases the rate of the reaction.
Then why would they have the same point on the graph? Is that just showing, because it said
What
progression?
same point?
If you go, can you go back, well, it says progression of reaction. then if you look at the bottom, the products and the reactants are at the same time, but they're the same phase.
Oh, okay. So this, you're saying that the distance on this axis is the same? Ah, this isn't time. Time is not a part of this graph at all. Very good point. I've never actually thought about that, but that could be really confusing. This graph just says we're at reactants, we're at products. This graph only focuses on the energy required between those. So this is completely irrelevant. Thank you very much for pointing that out. Does everyone see what she's talking about? That this is not time, this is just progress. Is it starting? Is it ending? Are we in between? And there's no relative time scale on any of these. Really good point. So, this Arrhenius equation, I hope that you guys did spend a little bit of time reading about it so you know what the different variables are. So we have our temperature in degrees Kelvin, and we have our activation energy in joules. What is R? Javante? It's a gas constant, and we're assuming standard temperature and pressure, so we use the standard gas constant, even though we're talking about different temperatures here. So if we were to plot how the rate constant changes with changing temperature, we get a really screwy, hard to predict line. We get an exponential relationship. So what do chemists like to do with graphs? Say again? We like to find some way to get a linear relationship. So what could we do to get a y equals mx plus b version of that relationship? Somehow talk about how temperature changing and rate constants are related to each other. So let's try taking the natural log of both sides. So we take the natural log of both sides. And then Shane, I'm probably going to mess up what we talked about yesterday. Well, how do we end up doing this? What was the... I literally just worked through this yesterday, and I'm blanking on... There we go. It's this, right? So you do natural log of a times b. It's the same as natural log of a plus b. Natural log of a plus natural log of b. So this is using rule of logs. That's just taking the natural log of both sides. And then what happens when we take the natural log of e to the something? Falls off the log, right? So this falls off the log. And then this cancels out. So if we're going to rewrite that, ln of k equals natural log of a minus ea over RT. Okay, so that still doesn't look like a straight line though, right? So let's take the stuff on the right side here, and let's say EA over R times 1 over time. Is everyone okay with that being the same? Need a negative in there, of course. And then if we rewrite that, we can say ln of k equals negative EA over R times 1 over T plus ln of A. Brianna?
Does it matter if you make it like negative EA over R times 1 over T, or if it's negative EA over T times 1 over R? Does that make a difference?
So why did I tease apart negative EA over R times 1 over T? Mia?
So you can get a slope like so.
So what are we going to plot? What's our x and our y in this graph?
X is 1 over T, and then the Y is natural log of K.
So what I did is I tried to simplify it so that we can see we have a y value here. We have a slope, and this is what our x values are going to be. And then this is our y-intercept. So this is just another way of looking at, well, if we change our activation energy, what should happen to that plot? If you change activation energy and this y equals mx plus b, what does that influence on the graph? What's that, Megan? Slope. Negative EA over R is our slope. So if we add a catalyst, does our activation energy go up or down? We add a catalyst, activation energy lowers. So does the slope get steeper or less steep? Lower slope means it gets less steep. So we should be able to do a lot of manipulation looking at if we are able to plot natural log of k versus 1 over t, we should be able to learn a lot about a reaction. How can I determine the activation energy if I had a plot of those? Let's say I looked at a whole bunch of different temperatures and I measured what the rate constant was. How could I determine the activation energy from one of those plots? And I think I actually have some of this worked out on future slides. So here are those two plots. Here's the rate constant versus temperature, not linear. Chemists don't like this. Here's the same data plotted natural log of k versus 1 over t. So if I have this data, how do I find the activation energy for this reaction? I didn't change the activation energy. I only changed temperature and measured the rate constant. Thomas? If we find the slope of this graph, we can automatically find what the activation energy for that reaction was. And I think the last thing that I want to show here is we can use this to determine the activation energy. Can we just look at the slope of k versus t? Why not?
Because you have to do the ln and the 1 over t.
So we'd have to find the natural log of k and compare that to 1 over t, find the slope using two of these data points here. Okay, so you guys have some practice problems. Are these on your worksheet? Okay, I'm going to post these questions online. There's 2 practice problems here. We're going to start class on Tuesday with nuclear chemistry. We're going to do a little bit of nuclear chemistry, and then we're going to jump right into equilibrium.
For the slope, do you still want us to use